This talk is on algebraic abstractions for concurrent separation logics. The semantic model of separation logic is the algebra of partial commutative monoids. Formally, partial commutative monoid, or PCM for short, is an algebra with partial binary operation, pronounced join, and a constant, pronounced unit. The join and unit are subject to commutativity, associativity, and the unit law, as is the case with regular monoids. The extra property comes from partiality of join, namely, whenever a join of two elements is defined, each of the elements is defined as well. When you think how the definition translates to separation logic, the intuition here is that the elements of the carrier model the private state of individual threads. Join models how the private states of two children combine into the state of the parent. The operation join is commutative and associative because the order of the threads in a thread pool is irrelevant for the computation. The operation join is partial to model that some state combinations are impossible. The unit element represents the empty private state. The canonical PCM in separation logic is that of heaps, which are finite maps from pointers to values. The join operation is the disjoint union of heaps. When the private heap of thread 1 on the left doesn't share any pointers with the private heap of the thread 2 on the right, they can be joined into private heap of a parent. The operation is undefined if the operand heaps have a pointer in common, thus modeling that the private heaps of two concurrent threads cannot share pointers. The unit is the empty heap with no pointers allocated. Modern work on separation logic uses PCMs to model host state in addition to heaps. Here I show the ownership PCM that models mutually exclusive locking. The value own signifies that a thread owns the lock, while the value not own, displayed as own with overbar, signifies that the thread does not own the lock. The join computes lock ownership of the parent thread from those of the children, and is given in the table. The own value is capturing and two own values cannot be joined, and the result is undefined to model exclusivity of locking. Two threads cannot own the lock simultaneously. The key contribution of our paper is morphisms of PCMs and how they are used in separation logic. The equations shown on the screen are the standard algebraic definition of morphism from monoid A to monoid B. The morphism preserves unit and distributes over join. As an example, take a function alpha that takes private state of a thread and computes lock ownership. Consider a thread 1 with its private state x. Say the thread does not own the lock. Now, there is also thread 2 with private state y. We can use alpha to compute ownership of the lock for thread 2 as well. Say thread 2 does not own the lock neither. When we join thread 1 and thread 2 into a parent, we expect that alpha computes ownership value from private state of the parent that is coherent with the computations carried out on the children. The join operation is partial and the joined values may not be defined. To ensure that the morphism is well behaved, we make the second property conditional. We associate with each morphism a separating relation. In practice, the separating relation relates private state of thread to private state of environment. In this talk, I will explore the concepts of morphisms and separating relations and show how the two concepts interact with standard algebraic constructions. Now, Let's see how morphisms and separating relations work in practice. Think a simple example like a lock. There is a method, lock, that acquires the ownership. Say we choose ticket lock algorithm due to Mellor-Cramy and Scott and inspired by Lampard's bakery algorithm. Ticket lock consists of two shared pointers, the ticket dispenser TDR and the display TSP. The thread that wishes to acquire the lock first atomically increments TDR. The thread then loops until the pointer DSP matches the value read from TDR. Intuitively, the ticket lock's workflow resembles the ticket queue management system that guides customers to a counter in a shop. Incrementing TDR corresponds to taking a new ticket from ticket dispenser, thus fixing a customer's position in the queue. Looping corresponds to awaiting the ticket's turn. Incrementing DSP signals on the display the next customer's turn. Next, let's see the structure of the host state. We will use the PCM of finite maps from positive natural numbers to labels drawn, served, and used to represent the host state of ticket lock. This PCM is an instance of the PCM of finite maps. Finite maps form a PCM with disjoint union as join and the empty map as unit. We already saw another instance, which is heaps. The PCM represents ticket lock as follows. Given a ticket, say 1, is drawn from dispenser and the thread is waiting to be called on the display to go to the counter. The next ticket may be drawn, that is ticket 2, which is also waiting. This situation can freely repeat. Once a thread with ticket 1 notices it was called on display, it updates the called ticket as served, and when it finishes at the counter, it updates its ticket to used. Similar situation repeats with ticket 2, except that the thread may be interleaved at the counter, with ticket 4 being drawn from the dispenser. We call such representation ticket map. Ticket map allows us to compute values of both the ticket dispenser and the display by morphisms. Since we are going to compute display with a morphism, we also need a range PCM. We are going to use a PCM over natural numbers with maximum as the binary operation. Positive natural numbers give rise to PCM structure under maximum. It is easy to see that maximum is commutative, associative, and preserves unit. Partiality is preserved trivially, as maximum is total on the carrier. Now, given a ticket map, we can compute the ticket called on the display by taking the maximum of numbers on tickets labeled as used plus 1. According to the workflow of ticket locks, upon finishing its turn with a lock, a thread holding the ticket T sets the display to T plus 1, called the next thread in the queue. Thus, the value of the display, which at that point denotes the currently called ticket, is one larger than the largest used ticket in X. The function psi is our first example of a morphism. The morphism psi is defined whenever the join of the domain PCM is. To check that psi preserves structure as we expect from a morphism, say there are two maps with ticket 1 and 3 and with ticket 2. Ticket 3 is being served, other tickets are used. Out of the first map, psi computes 2. Out of the second one, psi computes 3. Since 2 join 3 happens in the PCM of natural numbers under maximum, the result is 3. This is the same value as psi computes over join of the two maps. Before we can derive the specifications for lock, we need to annotate the programs with ghost code to mark manipulations with the ghost state. In our ambient type theory, the ghost code, displayed in gray, is formed by transitions of the state transition system. Transition works upon subjective state, that is state that distinguishes between private state of a thread, called self-state, and the aggregation of private states of all the other threads, called address state. These two components can be projected out of state, which we denote by _s for the self-state and _o for the address state. Locally, for a thread, state is thus a pair of self-state and address state. There is one important concept to introduce, that of morphism applied to global state. A morphism applied to global state is join of morphism applied to self and morphism applied to address state, or, due to the morphism property, a morphism applied to the join of self and address state. I will use notation psi hat to denote morphism psi applied to global state. Global state of two different threads in the same thread pool is the same. Recall that join is commutative and associative. The transition system consists of 3 transitions: take ticket transition, lock transition, and unlock transition. Each is a relation over the initial state S and the final state S prime, and defines one of the 3 basic changes that ticket lock programs can perform over the state. Just to illustrate how transitions work, I will focus on lock transition. The lock transition works with the ticket T that is currently on the display. The value T is computed by morphism psi from global state. The transition updates the ticket map at T from drawn to serve to model that the thread noticed its ticket called on the display and took its turn at the counter. This models taking the turn at the counter when a ticket is being displayed and completes the acquisition of the lock. Now we can decorate program lock and to illustrate when the various transitions are invoked to change the host components of the state. In the code, angle brackets signify the code executes atomically. Take ticket transition is then executed atomically with incrementing the ticket dispenser. The thread then waits until the drawn ticket appears on the display and then executes the lock transition to acquire the lock. With the internal state defined, we can next establish the specification of lock. The specification is intermediate because it specifies lock in terms of components of the underlying PCM using morphism psi, thus exposing the internal state of the ticket lock. Eventually, we will use this specification to derive a canonical, client-oriented specification of locking. The specification for lock says that initially the host ticket map in the private or self state is empty. Upon termination, we hold the ticket being displayed, and this ticket is labeled as serve in our map. Notice that the value of psi hat s in the post condition is stable under interference, as other threads cannot change the display because we hold the lock when we are being served. Formally, specifications are predicates over the state of the underlying state transition system. The predicate is formed as lambda abstraction over the variable representing state. I will drop the lambda where convenient. It is straightforward to obtain this specification from the definition of lock program. Taking ticket results in self state that contains a waiting ticket and bounds the display from above, while in the loop, last thread value of the global display is stored in Y and bounds actual global display from below. If the loop terminated, this ticket is being displayed. Finally, lock transition updates the ticket to serve. As customary in separation logic, this small footprint specification can be framed to any ticket map. Say we want to frame the previous specification with ticket map K. Let's see how framing carries through. We first split the self state into what is expected by the precondition of small footprint specification and the rest of the self state, which is the frame. Notice that the precondition works with formally different variables. That is, variables u on the second line and s on the third line. The thing is, we dropped the initial lambda in the specifications. As the private state in the specification is lambda abstracted, we can freely rename the variable. The same argument holds for the postcondition, similarly for the frame. Now we apply the frame rule and obtain the small footprint postcondition of lock program. The frame carries over unaltered. We merge the postcondition and the frame, and after some reordering, we obtain the frame postcondition. A seeming issue occurs in the value of the display. Psi hat is computed over different states, u and s respectively. In fact, this is not a problem, since global state over u and s are exactly the same due to the commutativity and associativity of join. One thing I would like to mention is that splitting the frame from the precondition and merging the postcondition and frame cannot be in general done abstractly. In the paper, we identify a class of invertible morphisms over invertible separating relations that allow such manipulations of specifications. The definition of invertibility is another key contribution of our work. Now, back to the specification. The framed specification is still an intermediate specification. That is, a specification in terms of the internal representation by ticket map. In the beginning of my talk, I mentioned the ownership PCMO. Ideally, we would like to have specification of lock in terms of the ownership PCM rather than ticket map. We can utilize a morphism alpha prime from ticket map PCM to ownership PCM to transform the intermediate specification into an abstract one. The question is, how do we define such morphism? We do it in steps. First, we define a morphism alpha. In the definition of alpha, one should think of X as the self-component of a thread. Then we define alpha such that the thread owns the lock if and only if it holds a ticket labeled serve in the self-ticket map. The issue with the definition is that alpha does not preserve structure on the whole domain. As stated, the transition system does not enforce exclusivity of locking, and there can be two tickets being served at the same time. For alpha to behave well, we need to preclude this situation. A formal way to say that alpha is well behaved is to associate it with the separating relation bottom alpha. The notation hash subscript serve signifies the number of tickets labeled serve in a ticket map. The definition directly captures that together X and Y contain at most one served ticket. We show in the paper that bottom alpha is indeed a separating relation, and moreover that hash subscript serve itself is a morphism composed out of map filter and map counter functions, both of which are morphisms. This demonstrates how algebraic definitions guide compositionality. To transform the specification in terms of the internal representation to the specification based in alpha, we must ensure that private state in the specification is in alpha's domain. We do so by attaching the property self-state bottom alpha related to the other state, to the pre and post condition. The additional property is preserved by all transitions, thus also by the lock program, and carries over. The remaining steps follow by unfolding the definition of alpha. This specification we have now is abstract, but we can still do better and get a more compact specification. To obtain the ultimately desired compact spec, our algebraic approach provides the sub-PCM construction. The construction quotients the PCM M by relation bottom alpha to obtain a sub-PCM MTL. It's essential for the sub-PCM construction that the condition by which we quotient out is a separating relation. Otherwise, join won't be commutative, associative, and admit a unit. But once we know that the condition is a separating relation, there is a generic construction of the sub-PCM. You can find details in the paper. Also, morphisms play a role in the construction and in relating a PCM and sub-PCM. As customary in algebraic definitions of substructures, the sub-PCM constructions comes with two morphisms, injection iota and retraction rho, that allow us to transfer values reasoning between object and subobject. We can transform the specification using alpha into a 1 using alpha prime that is defined by precomposition of alpha with injection. The condition self-state bottom alpha related to the other state transforms into definedness of the sub-PCM. The important thing to keep in mind here is that the previous specification was expressed in terms of alpha over PCM M, whereas the new specification works in terms of alpha prime over the sub-PCM MTL. This also makes definedness guaranteed as a property of state space and thus can be elided. This yields a compact specification in terms of the ownership PCM. And now for something completely different. What is in the paper? There are formal definitions starting with definition of partial commutative monoids. There are separating relations and there are algebraic constructions of PCMs and separating relations starting from simpler ones like Cartesian product of PCMs being a PCM and developing towards separating relation bottom alpha. Naturally, there is a formal definition of PCM morphisms and there are constructions involving morphisms starting with composition and products and ranging towards kernels and equalizers. With morphisms and separating relations, we can define sub-PCMs and their generic construction. Finally, there is a formal definition of invertibility, and we put invertibility into the context of standard treatment of separation logic, and in particular to concurrent abstract predicates, which are used in most modern separation logics. And finally, what is this paper about? Partial commutative monoids are the key algebraic structure for modeling ownership transfer. We show that PCMs possess a pleasant theory of morphisms, which extends standard algebraic approach to concurrent separation logics. We devise separating relations as domains where functions between PCMs are structure preserving. That is, separating relations capture partiality of morphisms. Morphisms and separating relations have direct use in specifications as the assertion language and they are used as abstraction mechanisms in proofs. Finally, our exposition of PCMs and their morphisms is natural. We recover standard algebraic constructions. For example, that of a subobject, a sub-PCM, or kernels and equalizers. We show that the constructions preserve structure. For example, composition of morphisms is a morphism, an equalizer of morphisms is a separating relation, and so on. This guides reusability and leads to compact specifications and compositional proofs. Well, that's all from me for now. I hope you find our work interesting, and please do get in touch if you want to know more.